ECC Hello everyone, welcome to the session. So we will start in a couple of minutes. I think most of the speakers are here and also the co-chair, Tom. So can you also make Tom a co-host, please, Julia? Thank you. So I will be back like in 5 minutes, but I think all of the speakers are present, or let's say most of the ones. Yeah, bye. So I will be back like in 2 to 3 minutes, and we will start like on prompt at 10:30. So Tom, you are around. If Tom is also around, my co-chair, so he's going to help me out while sharing the session. No? Oh, yeah. So let me provide you this kind of brief guidance rules that are provided to me by ECC organizers. So during the presentation, please do not open any videos. After the presentation, the author can open its video and microphone to answer the questions either from the chat board or directly interactively through this channel, to this video and audio channel. Please try to raise your hands so that I can give you the word, or just unmute yourself and ask a question directly once the author has answered one of these questions, one of the previous questions. Please try to ask questions. Okay, so this is like a usual problem in conferences, no questions. Now it's over Zoom, and I think it's a bit more difficult, more challenging. So, but now if you want, you can ask questions over the chat board if you don't feel comfortable in speaking, or just ask for a word and I'm going to give you a chance to ask a question directly to the author. It looks like all of our authors are around. So we have this kind of full house. So all papers will be presented anyway, but there will be also time for some questions and answers. Looking forward to see the papers and get some new idea about unmanned air vehicles. So we will start like in 2 minutes. So as I said, there will be like this kind of promo video in the beginning of the session, and after the promo video, we will start with our session directly.
Join our special session for a talk by Professor Duarte Antunes on teaching MATLAB with live scripts. MathWorks has various resources for online teaching. MATLAB Tech Talks are educational videos that you can leverage to supplement your teaching of engineering concepts. Feel free to check out our free video collection by visiting the link or scanning the QR code. With MATLAB Live Editor, you can create interactive exercises where descriptive text and executable code are combined in a single document. Using MATLAB Online, students can run these exercises from any web browser without needing to install MATLAB. You can save instruction time by leveraging the free interactive tutorials on MATLAB, Simulink, machine learning, deep learning, and Stateflow. For more information on available resources, please check out our website.
Okay, so MATLAB, pretty powerful. So let us start with this session without losing any time. So the first paper is like reconfigurable control of a class of multicopters. And let us see the presentation now.
Assalamu alaikum, ladies and gentlemen. I am Hafiz Zishan Iqbal Khan, and the title of my presentation is Reconfigurable Control of a Class of Multicopters. Before I formally start my presentation, let me briefly summarize the main contributions of this work. In this work, the notion of reduced controllability is introduced, which shows that even in the occurrence of some uncontrollable failures, it is still possible to control a reduced set of states. Based on that, a reconfigurable control scheme was presented for a generalized class of multicopters, namely coplanar multicopters. Here is a brief outline of the presentation. I will start with introduction and classification of coplanar multicopters and its mathematical modeling. Then I will discuss controllability of coplanar multicopters and their reconfigurable control scheme. In the end, I will discuss 6 simulation results followed by some concluding remarks. A multicopter can be defined as a flying vehicle in which lift is produced from 2 or more rotors. These multicopters are becoming very common for daily life applications due to their ease of construction and control and their hovering and VTOL capabilities as compared to their fixed wing counterparts. As the applications of multicopters are increasing, various complex and unique designs has evolved. For example, more number of rotors for heavier payloads and various novel configurations for agile maneuvering. As the application of multicopters are increasing, their performance requirements and safety constraints are getting more stringent, which not only requires better designs but also advanced control strategies with embedded safety constraints such as fault tolerance and collision avoidance, etc. Since rotors are prone to failure and damage, therefore some fault tolerance is usually desirable. However, failure of a rotor greatly reduces the controllability of a multicopter, which in turn puts severe limitations on the design of a fault-tolerant reconfigurable control system. A coplanar multicopter is a multicopter in which thrust vectors of all rotors are parallel in hover. This class of multicopter is quite general one. It includes almost all common configurations like these standard quad and hexa configuration. The dynamic model of coplanar multicopter can be briefly summarized like this using Euler angle based attitude representation. Here, x is the inertial velocity, v is its inertial position, phi is the vector of Euler angles, and omega is the angular rates. Total forces and moments of all end rotors on a general coplanar multicopters can be written like this, considering the top view of a coplanar multicopter, where Rn is the distance from nth rotor to the CG of multicopter, and delta is its angle from x-axis. Here, kappa mu is the torque coefficient, and gamma is the direction of rotation, which is +1 for clockwise for counterclockwise rotating rotors, and gamma equals to -1 for clockwise rotors. Before proceeding further, let me briefly introduce the notation. The configuration is encoded as a string of length n with p for gamma equal to +1 and n for gamma equal to -1. For example, this configuration here represent Pn, 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 while this is Pp, Nn, and Pn. Since in coplanar multicopter, maximum of 4 variables can be controlled at a time, which are usually either its attitude and altitude or position and heading. Horizontal position dynamics doesn't account much for its controllability analysis, since it can be considered as a set of outer loops in roll and pitch angles. Therefore, for controllability analysis, only attitude and altitude dynamics are considered. Linearizing about hover conditions yield this linear model, which will be used to assess the controllability. One main issue here is that the input u or tau is bounded but not symmetric about the origin, because rotors produce thrust only in one direction. For systems like this, the standard ramp condition of LKI controllability is not sufficient anymore. Using positive controllability theory, you presented these necessary and sufficient conditions for controllability and defined a controllability measure as available control authority index like this. And he showed that a multicopter is controllable if and only if its controllability matrix is of full rank and its available control authority index is positive. So here is the results of controllability for single or multiple rotor failures. This shows that the PN configuration hexacopter is not controllable for any rotor failure. However, PN and PN configuration is controllable for single rotor failures of rotor 1 to 4, while not controllable for 5 and 6. It is also controllable for rotor 1 and 3 or 2 and 4 combined failed. To further elaborate this, consider both configuration with rotor 1 failed. The most intuitive solution in this scenario would be to turn off the opposite rotor, that is the fourth one, to get quadcopter-like configuration. But to be controllable, these resulting configurations must be able to independently produce thrust in all 3 moments. Although both can produce thrust and rolling motion, but the PPN configuration cannot produce pitch and yaw motion independently, thus only one of these channels can be controlled, in contrast to this PPN and PN configuration. As we have seen, there are quite a few cases in which rotor failure results in uncontrollable system, which puts severe limitations on fault tolerance control. Therefore, though all states are not controllable, it would be of great importance if a critical subset of states can be controlled. This can protect multi-copter from crashing and making it possible to land multi-copter safely in such critical scenarios. Considering the linearized model again and assuming the inertia matrix as diagonal, which it usually is, it can be written as in terms of these four decoupled systems. Now let's define a reduced set of systems by considering only 3 of these at a time. Here alpha is the index representing the channel which is not included in the reduced linear model. Like available control authority, we defined a available reduced control authority index and showed that a reduced system is controllable if and only if its rank of its controllability matrix is full, that is 6, and its row is positive. Now consider the reduced controllability of both hexacopter configuration. It is shown that even though PN configuration, any rotor failure is not fully controllable. Yet if we choose to not control theta or psi, the remaining states become controllable in hover for any rotor failure. Also for this PPNN configuration, failures in rotor 5 and 6 were not controllable, but if we choose to not control any of the attitude angles, then this remaining set of states become controllable. Here it must be noted that reduced controllability is defined only for hover case, so it doesn't give any insight about non-hover conditions. These limitations of analysis become very significant, especially if we let either phi or theta uncontrolled, because with that multi-copter goes out of hover condition almost instantaneously, which may cause instability. But we can let psi uncontrolled and then it is possible to safely land the spinning multi-copter. The main idea behind this scheme is to divide the reconfigurable control scheme into 3 parts. The baseline control law, which is in this case a robust NDI, nonlinear dynamic inversion based control, fault detection and isolation, and most importantly the constraint control allocation, using which fault tolerance in the presence of both controllable and uncontrollable cases is achieved. Here is the complete block diagram of the control scheme. These are the NDI controls law for each loop. Faults can be defined as an unpermitted deviation from standard conditions or from acceptable conditions in a parameter or a characteristic property of a system. Faults can be of different types, but in this work we are focused on rotor failures, which are a type of actuator faults. We have used a very simple FTI scheme to detect and isolate the failed rotors so that they can be compensated in control allocation scheme. Here is the block diagram of the scheme. Basic idea is to compute the residuals of individual rotor thrusts, and if that residual increases certain threshold, then the corresponding rotor is declared as faulty, otherwise not. The control allocation problem for a coplanar multi-copter can be written like this linear control allocation problem. Here epsilons are rotor health, which is 1 for normal condition and 0 for a failed rotor. The basic idea is to distribute control commands among only healthy rotors, and we use the RPI methods, which distribute commands multiple times to avoid any saturations whenever possible. For uncontrollable failures, the pre-decided reduced set of commands are distributed while letting the uncontrolled channel free. To demonstrate the fault tolerance of the proposed scheme in the presence of controllable and uncontrollable rotor failures, different rotors are failed in nonlinear simulation of a PN type configuration, and here is the reference trajectory for which the simulation was performed. For controllable failures during climb phase, rotor 1 is disabled at 7 seconds, and at 60 seconds rotor 3 were failed during forward flight. So, as this result shows very good trajectory tracking performance with reasonable variations in attitude and body rates. These are the commands and actual rotor RPMs. Similarly, for uncontrollable rotor failures, as we know that for this PP and NPN configuration, rotor 5 and rotor 6 failure results in uncontrollable configuration. Also, from available reduced control authority, we know that in these rotor 5 and rotor 6 failures, if we let any of the attitude channel uncontrolled, then the resulting reduced system is controllable. So for this case, at 60 seconds during forward flight phase, rotor 5 is failed and control scheme is reconfigured such that it lets yaw channel uncontrolled. Results shows a very good trajectory tracking performance with damped but oscillatory roll and pitch behavior, but oscillations are in reasonable bounds. However, the yaw angle being uncontrolled increases without bound at a constant rate. This value of steady yaw rate is purely determined by multicopter's aerodynamics and cannot be manipulated by the other channel's controllers if yaw is left free. These are the rotor RPMs. So, the concluding remarks. In this work, a reconfigurable control scheme for coplanar multicopters is presented. A notion of reduced controllability is introduced, and it was shown that even in some uncontrollable failures, it is still possible to control a reduced set of states, which allows to recover and safely land the multicopter, provided that the reduced controllability is present. For an example of hexacopter, it was demonstrated that the proposed control scheme gives satisfactory trajectory tracking in both controllable and uncontrollable scenarios. Thank you. Any questions?
Okay, so thanks for the presentation. So I think the author is here. So if you have any questions, you can directly ask to the author. So the first author is here, Hafiz, I think, yes.
Hello.
Hello, Hafiz. So let's see if you have any questions from the audience. Do we have any questions? So as usual, no questions. So I have to ask, I think, a couple of them. So thanks for the nice work. So I'm just curious about a couple of points. So basically, if I didn't understand this wrong, you have this kind of over-actuated system, right? So you have this kind of extra degree of freedoms. You are this kind of controllability, and with respect to this kind of controllability, you are doing this kind of control allocation. So in the case of a fault, how should I allocate my control signal to the final actuators? So the thing that I'm curious is that, have you also investigated something like with performance? Because we have these kind of different configurations like NP and NP and so on. So has a certain configuration has an advantage over another one if under the assumption that both of them are controllable?
Basically, in nominal case, when any rotor is not failed, both configuration can perform similarly. However, if some of rotors failed, the configuration is hugely depend on the controllability of the multicopter. As we showed that the in PP and NPN configuration is controllable even after some failures, while the other one, PNPN configuration, is not controllable even with any of the failures. Regarding the performance of nominal systems, the PNPN configuration, which is not controllable in failure case, but has more control authority in nominal case. However, the one which has controllable in failure case is slightly less control authority in nominal case, but it is controllable in both cases.
So basically, one more thing, you have this kind of 6 quads. So you have these kind of 6 planners, right? Yeah, 6 ones. So you have
6 rotors.
Yeah. So in the simulation study, I think you only focused on the failure of a single one.
Result shows both failure of a single and 2 rotors.
2 rotors. So basically, even if there are two rotors failed, you have like 4 rotors left. So this is like almost a quadcopter now, right? So have you ever done some simulations or analysis when there is a failure more than 3 or 4? So when the system is actually transforming to this kind of under-actuated system.
Then it will not remain controllable. For a quadcopter configuration, if even a single rotor failed, the resulting 3 rotors cannot control all 4 degrees of freedom.
Yeah, obviously. I mean, if you are like under-actuated, then you have to leave one of these kind of degrees free eventually. But have you done some simulations regarding this one? Because you have now this kind of over-actuated system, and if 3 of these kind of rotors are failing, then you are converging basically to this kind of under-actuated system.
The uncontrollable failure
would be like an issue.
The uncontrollable failure case can be applied to this for 3 rotor failures, resulting in 3 rotors of a quadcopter configuration. We can apply similar scheme by letting yaw uncontrolled, so the spinning quadcopter can be landed safely.
Okay, that's nice.
Like the one we employed in the last results.
Okay. So we have like 3 more minutes. Any other questions from the audience? Maybe my co-chair, Tom, want to contribute with something?
Can you hear me?
Yeah, fine.
Okay, great. Yeah, so in a sense here, you're also trying to deal with under-actuation problem when you have several failures. And I was thinking more like, what about if you've seen anything into geometric control? Like I can see you have the controllers that you have before the control allocation scheme and the fault detection scheme. It's nested loops, and if it could help to replace that with some more other controllers, with for instance from geometric control theory, that can.
Yeah, exactly. I am working on geometric control theory, but basically, in under-actuated case, you can do motion planning using Lie brackets and so on. However, we need a closed loop stability, so we cannot do a motion planning for unknown type of reference trajectories. So we can try. We are working on geometric control.
Okay.
All right. Thank you, Tom, for the contribution. And I think we are now up to time for the next one. So, Tom.
Yes. So the next speaker is going to be Advait Datar from Hamburg University of Technology, and they'll be presenting their work on flocking towards the source, indoor experiments with quadrotors.
Welcome everyone. My name is Advait Datar, and I will talk today about flocking algorithms to address the source-seeking problem and some experiments with quadrotors. This work is done in collaboration with Peter Paulsen and Professor Herbert Werner at the Technical University of Hamburg. Before we jump into the details, we'll first motivate the source-seeking problem by considering 2 scenarios. On the left, you see the radioactivity level contour plot after the Fukushima disaster. And on the right, you see an oil spill scenario. One can imagine that in these scenarios, we can deploy a fleet of quadrotors or say underwater robots that could locate regions with highest concentrations of radioactivity or that of oil concentration. With such scenarios in mind, we can now define the source-seeking problem in an abstract setting. We consider a group of N agents, which could be underwater robots or quadrotors, that are deployed in some region of interest. Each agent is equipped with a position measurement sensor, a communication device, a concentration measurement sensor, and some computation capabilities that allow it to complete the source-seeking task. The problem can then be defined as to design distributed control algorithms that cause the group of agents to flock towards the source. So we treat the source-seeking problem as a minimization problem. Note, however, that the practical problem involves finding the region with the highest strength of the field, such as radioactivity, but we can invert the sign on the cost to write it as a minimization problem. Now, momentum methods have been around in the optimization literature and are known to speed up convergence rates and dampen oscillations. These methods are all the more interesting to us because our mobile robots naturally have momentum and inertia to them, and the dynamics of these methods can be easily augmented with the flocking dynamics. We would like to note here that the analysis that we will pursue later will be in the continuous time setting instead of a discrete time setting, and that's because we want to prove asymptotic properties which are slightly easier to be shown in the continuous time, and we want to avoid a sort of tangential discussion on step size selection and so on. Now let's make things concrete by considering the Newton method with momentum. We have an f which is strongly convex and twice differentiable, whose minimizer we seek. The standard Newton iteration is given by the expression in 1, where nabla squared f is the Hessian and nabla f is the gradient evaluated at instances xk. Now we can write an analogous continuous time version of these dynamics as shown in 2. Where we can see that if we now Euler discretize the dynamics in 2 with a step size of alpha, we obtain the dynamics in 1. Now the trick here in momentum methods is to add momentum to these first order dynamics. This is done by adding an mx double dot term to these dynamics to obtain the equation as in 3. We can rewrite the second order differential equation in 3 as a system of first order differential equations by defining a new variable v, which is defined as x dot. Now we keep this in mind because we would later want to augment our flocking framework by adding this sort of forcing term here. Before we do that, let's make clear what we mean by flocking dynamics. So flocking or flocking dynamics is basically an attempt to explain the emergent behavior that is seen in large groups of animals, such as the flock of birds that you see in the left picture or schools of fish. So there are multiple particle-based models that try to explain this emergent behavior by simple rules followed by each agent. One such model was proposed by Craig Reynolds in 1987, where he postulated that if each agent would follow 3 simple rules, which he called cohesion, separation, and alignment, it would lead to an emergent behavior of the group. These 3 rules basically mean that each agent tries to stay close to its neighbors, tries to avoid collision with its neighbors, and tries to align its own velocity with the velocity of its neighbors. When written in precise mathematical form, we obtain flocking dynamics as in 8, where q is the position and p is the velocity. So this term here can be seen as a forcing term because p dot is acceleration. V here denotes the particle-particle interaction field, and one can think of this as a force field. An example of a potential field is that of a gravitational field. However, while simulating planetary motion under gravitation, we will not have these 2 terms. These 2 terms here come from the alignment rule, which says that each agent tries to match its own velocity with the velocity of its neighbors. That is this term, where L is the Laplacian matrix. And this term comes mainly due to the damping or some friction involved in these agents. Now, observing these flocking dynamics and recalling what we saw in the momentum-based Newton method in the continuous time setting earlier, we can add a forcing term to these flocking dynamics, such as here, where psi now is the underlying source field, which we assume to be smooth enough to have these gradients and Hessians well-defined and convex. Now, in order to show that this is a good idea, we have the following theorem, which analyzes the dynamics shown here. So the theorem says that if psi is twice differentiable and convex, these dynamics are stable, meaning that the trajectories remain bounded for all times. Moreover, using Lassalle's invariance principle, we can show that the trajectories converge for all initial conditions to the largest invariant set within calligraphic W, which is given here. Let's quickly look at the proof, which follows standard dissipativity-based arguments. We can define an energy type function here as shown here, where this term is basically the kinetic energy. This term is the potential energy due to interactions amongst agents, and this term is the potential energy due to the external source, the external force field. Now we can differentiate this equation to obtain that E dot is non-positive, meaning that E is non-increasing. This implies that E at any time t is upper bounded by E at time 0 for all times, which implies then the boundedness of trajectories. So this is Lyapunov stability, or stability in the sense of Lyapunov. In order to prove asymptotic stability, we need Lassalle's invariance principle, by which then we can show that all trajectories converge to the largest invariant set contained in W. For a special case of quadratic fields, we have the following corollary. Now, this says that if additionally psi is strictly convex, quadratic, and has a unique minimum located at QS, then the center of mass of the agents, which is basically just the average of all agents, converges asymptotically to this source. In order to discuss experimental results, we should first talk about the plausibility of assumptions that we made for our theoretical analysis. We made 3 assumptions. A1, agents were modeled as double integrators. Assumption 2 was that the scalar field is assumed to be convex and twice differentiable. We also assumed that each agent had access to the gradient and the Hessian evaluated at the agent location. Now, in order to make the first assumption plausible, we first designed a local velocity controller which ran at 100 Hertz in the velocity loop, which is shown here as GWell. We tested the tracking performance of GWell by trying out different p-desired trajectories, where p-desired means the desired velocity trajectories. Because the flocking loop is running slower at 20 Hertz, we observed that the performance of GWell under reasonable p-desired trajectories that could come out of flocking could be approximated by a single integrator, which meant that the model of our quadrotor as a double integrator was reasonable for our setup. The next assumption that we made was that of convexity and differentiability of the fields. Well, we are aware that most of the fields in practice would not be convex and moreover not even differentiable perhaps. For such situations, we believe one could find smooth approximations or smooth local approximations and use the gradient and Hessians of these approximations in case of non-differentiability. Whereas for non-convexity, one can look at these results as local results instead of global ones. Moreover, we also did some experimental tests with non-convex fields to see the applicability of the algorithms in such scenarios. We, however, like to point out that this is still ongoing work and we're not yet completely clear on how to treat non-differentiable and non-convex fields. The third assumption that we made was that each agent has access to the gradient and Hessian information. In order to make this assumption plausible, or to test the plausibility of this assumption, we injected random noise centered about 0 and with a magnitude of ±5%. of that of the field strength to see the errors that we obtained in the Newton and in the steepest descent direction. Well, because the gradient and the Hessians are not available, we solved two small least squares problems on board and got these estimates. We used a heuristic here that whenever the estimated Hessian was not positive definite, we simply used the steepest descent direction. Now, this figure shows a histogram of errors in degrees for a sample experiment. We see that for most of the samples, the error lies between plus minus 45 degrees, which says that in spite of this injected noise in the measurement, the agent is able to locate the correct quadrant in which the source lies and thereby move towards it. Now, before we go to the experimental results, let's look at the setup that we have in our lab. The left figure shows a schematic of the indoor positioning system that we have. Each tripod has at the top and at the bottom an anchor which acts so the system together acts like an indoor GPS system. On the right, you see the Crazyflie 2.1 experimental platform. Both these hardware setups being developed and sold by the company BitCraze. Because the software on Crazyflie is open source, we were able to code our peer-to-peer communication protocol so that each Crazyflie could talk to its neighbors. Additionally, because there's no scalar field involved in our experiment, we had a virtual scalar field, and we gave each Crazyflie the value of the field based on its location artificially. Now let's look at the experimental results. So to conclude, we've proposed a distributed control algorithm that addresses the source-seeking problem. We theoretically analyzed the convergence properties of the proposed algorithm and then presented experimental validation with quadrotor experiments. With that, I thank you for your attention, and I'll be happy to try and answer your questions.
Okay, so thank you for the presentation. And if there's any questions from chat, keep in mind that down in the chat, you need to select to everyone, or at least to one of the chairs, so we can see the questions being sent. Yeah, or use the raise hand option. Is the author here? I'll invite you.
I'm here.
Okay, cool. So I think I can start maybe with a question. So the flocking algorithm provides the local controller on the quadrotor with a desired position, right?
Yes, so exactly.
Yes. And this output from the flocking behavior also depends on the measurements or the information that the vehicle, the quadrotor, receives from nearby neighbors, right? Their position and
yes,
clusters.
that's correct. Yes.
Yeah. So if we were to consider that there could be faults on these quadrotors, right? Let's say one of the quadrotors fails and leaves kind of the formation, or let's say there are disturbances or measurement errors, right? Some kind of issues like these. Have you looked at if it makes sense to try to include these kind of extra behaviors in the flocking algorithm, or if these things that are better suited to be handled by the local controllers on the quadrotors?
Yeah, thanks a lot. That's an interesting question. So I'd first like to point out that the flocking algorithm is sort of robust to agent failures. So if sort of an agent drops out, that's no problem. The others would accommodate and fill in this empty spot. So that's really a failure of one agent is not propagating throughout the network. However, one could try and look into sort of aggressive behaviors caused by these faulty agents, and that we've not yet looked at, but that's definitely interesting. And one could sort of figure out that one of the agents is aggressively maneuvering and change the interaction field with such aggressive agents. But that's not what we looked at for this work, but that's definitely interesting.
Yeah. For instance, you do include like the alignment with the velocity.
Yes, exactly.
So
yes.
Yeah. So if one quadrotor is failing, it will actually have a velocity that could impact the formation.
Yeah, that's quite definitely true. So one interesting observation is also that we see in animals is that if we have sort of a mother child pair, we have different interactions between these pairs. So we, in our work, assume the same interaction between all agents. So we have only one kind of agents throughout the network, but we could sort of differentiate into different classes of agents and then use what you just said. Yeah. Thanks.
Okay. Yeah. Is there any other questions?
I mean, I can just ask this kind of simple question, because in the beginning of your slides, it was like the motivation was like this kind of outdoor environments, but eventually we convert to indoor environments. So how would you project to implement the proposed structure in an outdoor environment?
So the main reason for doing experiments indoor environment was to have good control of different variables. So that was the key. Well, the assumptions that we have even in the indoor setting are that we have position measurements, which could be obtained via GPS. If GPS is not available, for example, for underwater agents, one could have sort of a localized anchors placed on nearby ships, and then have some localization algorithms running on the agents. Another effect that we did not consider in the indoor environment was wind gusts, which could also be analyzed in an indoor environment by basically just artificially perturbing one agent. So we did indoor experiments mainly to have control of different variables to study the effect.
Okay, that's nice. So I think we have to rush for the next presentation, Tom.
Yes.
Thank you for the presentation. And
thank you.
So the next paper will be attraction domain estimation of linear controllers for the altitude control of VTOL vehicles. And I think the rest is coming from here. Okay, we can run the video, I think.
Hello, and welcome to the presentation of our article called Attraction Domain Estimation of Linear Controllers for the Attitude Control of VTOL Vehicles, and more especially the PPI control of a quadrotor. The main topic of this presentation will be the attitude control of vertical takeoff and landing vehicles. Here is an illustration of our experimental VTOL vehicle, which is an open source quadrotor called BitCrazy. The control of VTOL vehicles has been quite well studied in the literature. It has been shown that these vehicles present some kinds of nonlinearities in their dynamical behavior, and that they can be controlled using linear or nonlinear controllers, depending on the degree of performance that we want to achieve with the controller. Here, we'll be interested by the linear controllers that are implemented on the CrazyFly. These linear controllers were designed using a linearization of the nonlinear model of the quadrotor at an equilibrium point. In theory, we can only guarantee that these linear controllers will stabilize the quadrotor close to the linearization point. But in practice, if we fly the quadrotor, we can observe a relatively large flight domain. So the question that we will try to answer today is, how large is this flight domain? For our study, we reused the original CrazyFly control structure, which is a cascade structure. We have an inner controller for the angular velocities and an outer controller for the attitude angles of the quadrotor. In each controller block, we have 3 PID controllers, one for each rotation axis of the quadrotor. This control structure is quite common in the literature and relies on the assumption that the quadrotor will fly close to the hover point, which is the point where the angular velocities and the attitude angles are 0. Indeed, if we linearize the model at this hover point, we can observe that the dynamics are cascaded and that there is a decoupling between the control axis of the quadrotor. So we reuse this control structure and we tune again the PID controllers using standard frequency design techniques in order to achieve better performance than the original controllers. So here we present some simulations where our linear controllers are applied on the linear model of the quadrotor in blue and on the full nonlinear model in red. We can observe on the right that for some specific set points, the linear model will remain stable, whereas the nonlinear model is unstable. The linear model was the model used to design the controllers, and the nonlinear model is the one which will be closer to the reality. So the question is how to ensure that no instability will occur during flight, meaning which are the limits of the set points that we can give to our controllers without causing any instability in the flight. So to answer that, we need to estimate the attraction domain of our linear controllers. So a classical tool to study the attraction domain of controllers is the Lyapunov stability framework. Basically, we'll search for a Lyapunov function that will characterize the attraction domain. So the classical approach will be to analytically search for a Lyapunov function given our system model and the control law. For the case of the quadrotor, this process may be complex and it may require to add additional terms in the control law in order to simplify the equations. So this process wasn't interesting for us because we wanted a systematic approach to study the strictly PID controllers that are implemented in the CrazyFly. So our approach was to consider the search for Lyapunov function as a convex optimization problem based on linear matrix inequalities. We believe that this approach provides a more systematic method for proving the system stability, as it is independent of the control law and doesn't need to add additional terms in it. So we'll define the state of our system as a combination of the angular velocities and the attitude angles of the quadrotor. And in the following, we'll talk about the equilibrium hover point of the quadrotor as the origin of our system where the state equals 0. So the objectives of our stability analysis will be to characterize this origin point. We want to determine its stability, and more importantly in this case, we'll want to determine its attraction domain, meaning the set of initial conditions such that the state of our system will tend to 0 when time tends to infinity. So the nonlinear model of the quadrator can be written as represented here. The angular velocities are noted omega, and the attitude angles of the quadrator roll pitch u are noted phi, theta, and psi, and u are the control inputs. This model can be written in a more compact form as equation 1, where the matrix A of x is the sum of a matrix A of theta of x, which represents the variations due to the angles in the nonlinear model, and A is K of x, which is a skew-symmetric matrix representing the couplings that we have between the angular velocities. So we'll take a classical Lyapunov function, which is a quadratic function defined for x taken in a subset of Rn called BR. The Lyapunov theory will tell us that the origin of our system is locally asymptotically stable if we can find a P matrix such that the inequality 2 is verified. And then we can say that the ellipsoid epsilon P, defined here, is situated inside the attraction domain of our system. So this ellipsoid epsilon P will represent our estimate of the attraction domain. So the problem with the inequality 2 is that it depends on the state x taken in BR. So instead of having only one inequality, we have an infinite number of inequalities to verify. So we cannot solve this problem numerically because of this infinite number of inequalities. So the objective of our work in the following will be to make this problem finite. So here we present some key steps that we use to make this problem solvable numerically. First, we will replace the A matrix by the sum A of delta of x plus A sk of x. And then we'll treat independently the angles time varying part from the skew-symmetric part of our model. For the skew-symmetric part, we'll apply a classical robust control technique, which is to add an equality condition in our optimization problem in order to cancel the skew-symmetric part from the equation 3. Then for the angles time varying part, we found a way to write the matrix A of delta of x as a linear fractional representation, which is a function of a block diagonal matrix delta of x, which is given in the equation 4 and 5. This block diagonal matrix delta of x will represent the nonlinear variations due to the angles in our model. So we define the set BR, which is a subset of Rn, as a set where the roll and pitch angles component of the states are bounded. This makes sense because usually we'll want our quadrator to achieve a relatively moderate flight domain where its pitch and roll angles are limited in the range of 25 or 30 degrees. So for this set BR and for the specific structure of the variation delta of x presented before, we found a way to characterize this variation delta of x with a constant matrix W. So this constant matrix W is given in equation 8. It is a function of the roll and pitch angles bounds from the set BR. And it is also a function of different optimization variables, such as U, S, W, and T. Finally, we obtain our optimization problem, where our optimization program will try to find the P and W matrices such that the following equations are verified. The first inequality corresponds to the derivative of our Lyapunov function that we had before. We have the P matrix, which is the P matrix from our Lyapunov function, and the W matrix, which is the matrix that we use to characterize the variations of the angles in our nonlinear model. Then we have the equation 10, which is the equality that we add in our optimization program in order to cancel the skew symmetric part from our problem. And finally, the equation 11 is here to ensure that the ellipsoid, which represents our estimate of the attraction domain of our system, will be bounded by the roll and pitch bounds from the set BR. So then finally, this optimization program will ensure that the ellipsoid epsilon P is situated inside the attraction domain, and so it will give us an estimate of this attraction domain. So we applied this optimization program in order to study the stability of the crazy fly when it is controlled by our linear controllers. Here we will present on the illustration the roll and pitch bounds of the set BR in black, and our ellipsoid is projected here in blue. So we also plot some trajectories of our system in red. We can see that for initial conditions taken in the ellipsoid epsilon P, the state of our system will return to 0 as time tends to infinity. So we found that the linear controllers that we designed at Hoover Point were able to stabilize the nonlinear model of the crazy fly for angles up to 30 degrees. So in conclusion, we presented here a method to estimate the attraction domain of our controllers around Hoover Point. We considered here the Lyapunov function search as an optimization problem with linear matrix inequalities constraints. We believe that our contributions are the optimization problem formulation, which was here to estimate the attraction domain of our system, and the quadrature-specific matrix W, which was the key to make this optimization problem solvable numerically. Finally, for the crazy fly application, we found that the linear controllers that we designed at Hoover Point were able to stabilize the quadrature for angles up to 30 degrees. Thank you for your attention.
Oh, all right. So I'm here. So if we have any questions from the audience, we have Walter here. So any questions regarding the presentation? We have a couple of minutes, 5 minutes for Q&As. Okay, so if not, I have just a little small one, I would say. So basically you use this kind of hovering mode to extract a linear model and then analyzed all this kind of vertical takeoff analysis, right? Model.
Yeah, so we linearize the model at the hover point.
Okay, so at hover point, what we know that small angle condition is necessary, right?
Yeah.
So basically, then you ended up again with this kind of small angle condition.
Yeah, I mean,
this is like you completed the circle, I think. Is it something like this? So because at the Hoover,
yeah.
I mean, I know that I need small angles, but the result of the paper is like, yes, you need small angles. I mean,
yeah, but the question was how much small angles? I mean, 30 degrees, it's not so much small for the roll and pitch angles.
Exactly.
It characterizes a quite classical flight domain for the quadrotor. And the objective here was to use a really common approach to linearize the model and to design PID controllers. And to be sure that the system will be stable without having a physical drone to test the results. So because we wanted to have like a design condition that we could use later on different quadrotors that maybe we will not have physically to test.
So in the design of the PI controllers, have you taken account any performance indexes like settling time, overshoot, or root mean square error? So how do you end up with these kind of, I mean, extra performance criteria, I mean, excluding the stability issue?
Yeah, so we didn't really talk about this in the article or the presentation, but so the performance criterion that we used were frequency design criterions, such as bandwidth and so settling time in time domain, but the design was made in a frequency design.
Okay. So any other questions? I think we are not much ahead, so it is just like Tom, Thor, and Erdal, and all family fates.
I kind of have
a
small question. So you did the hover condition and you get the angles. It's kind of like a restriction on the angles for the controller to kind of ensure asymptotic stability, right?
Yeah.
And often when we make these in these physical systems, in these cascaded controllers, the output of the velocity pit controller has to be converted to desired angles, right? And usually when you do this conversion, you need to do some kind of saturation that you don't ask for too large angles. So I guess this work here kind of gives you how you need to saturate the output for the pit velocity into the angle, desired angle, to convert into desired angles.
Yeah, indeed. In fact, on the CrazyFly, which is an open source quadrotor, we have these kinds of limits on the angles, but we didn't know how they were set in the program. I think the limits are 20 degrees for the angles, but we didn't have any proof that these were the right limits that we should give. So that was a way to verify that and to put our limits.
Yeah.
Right.
So yeah, I think we're thank you for that presentation and answering those questions. The next presentation will be by I suppose the chair of the session. And it's on real-time leader-follower formation control of nano quadcopters in the framework of ratio control.
Hello, I am Tufan Kumbasar, and I'm going to present a paper entitled Real-Time Leader-Follower Formation Control of Nano Quadcopters in the Framework of Ratio Control. The paper is organized as usual. I will first present the motivation of this study, and then I will talk about the ratio control problem in formation control. Afterwards, I will present a novel ratio station-based formation control structure for UAVs and validate its performance in a real-time application. Finally, I will provide the driven conclusions of the study. As we all know, UAVs nowadays are widely employed in military and commercial applications, and especially there is a focus on multi-agent UAVs. In multi-agent UAVs, there are various tasks to be handled, such as moving the center of mass of the formation, maintaining the relative positions, avoiding obstacles, and if necessary, splitting the formation. In literature, there are various studies handling the control design problem with various communication topologies. More specifically, for distance-based formation control tasks, we can group the controllers as symmetric and asymmetric controllers. In symmetric formation control structures, there is a joint effort of both agents to maintain the relative distance with a bidirectional communication topology, whereas in asymmetric formation control structures, only one of the agents tries actively to maintain the relative position with a directional communication topology. In this paper, basically, we are going to revisit the formation control problem in the framework of ratio control. We will show that the ratio control problem is identical to the one of formation control. Through investigation, we will show that widely employed ratio stations define directional or bidirectional communication topologies. Thus, we will conclude that they can be seen as symmetric and asymmetric formation control structures. In the light of the results, we will propose and evaluate a novel ratio station-based formation control structure in a real-world environment. Let us start with the ratio control problem in formation control. So the basic problem definition of a distance-based formation task can be simply defined as the difference between the outputs of two agents. If we now reformulate this problem with a ratio A, basically we can conclude that in formation control, it is desired to maintain this ratio A during the motion. This problem definition is identical to the one of a ratio control system. As we all know, a ratio control problem is to synchronize two control loops so that a desired ratio between them is retained regardless of reference variations and disturbances. In this context, let us first examine the parallel ratio station structure. The parallel ratio station structure is an open loop approach. It's simple. Basically, there are two independent control loops, no interactions between these control loops. Thus, although it is pretty simple, it has certain disadvantages, since the ratio cannot be kept during reference variations and in presence of disturbances employing the first and second control loop. In the framework of formation control, we can represent the structure with an independent communication topology as there is no information shared. Obviously, with this kind of a structure, the relative distance during motion cannot be kept in a multi-agent system. The second structure is the series ratio station structure. In this structure, basically the output of the first loop is generating the reference of the second loop. Thus, the dynamics of the first loop are quite important. If they are too slow, the ratio cannot be kept during reference variation. An equivalent communication topology can be represented for the series ratio station structure in a master-slave representation. Thus, we will end up with a direction communication topology. The series ratio station structure can be seen as an asymmetric formation control structure, since only one of the agents actively tries to maintain the relative distance. The third one is the cross-limited ratio control structure. In this structure, the references are generated by using the feedback information of both loops via max and min operations. The equivalent communication topology in this case is a bidirectional one, and thus the controller can be seen as a symmetric formation control structure. This formation control structure is pretty sensitive to measurement noise due to the deployment of max-min operations, and thus we might see this kind of chattering effect in the generation of reference signals. The fourth one is the blend station one. In this structure, the reference and output of the first loop is blended with a parameter gamma, which can take values between 0 and 1. In this structure, if gamma is equal to 0, we will end up with a parallel ratio station structure, and if gamma is equal to 1, we will end up with a series ratio station structure. For any values between 0 and 1, we will end up with a combination of the parallel and series ratio station structure, basically a hybrid. The equal communication topology can be seen as a directional communication topology. However, the output of the first agent is transferred to the second one with a certain degree, which depends on the value of gamma. The resulting formation control structure can be seen as an asymmetric one, and since it is basically blending a parallel one and a series one, it inherits the advantages and disadvantages of the parallel and series ratio stations. The final one is the cross-coupled ratio station structure. In this structure, the outputs and reference signals of both control loops are dynamically blended with two filters, F1s and F2s. In the cited paper, it is suggested to set F1s as beta and F2s with a dynamic structure as presented on the slide. The equivalent communication topology is a bidirectional, and both Y1 and Y2 values are shared with a certain degree, which depends on the value of beta. The resulting formation control structure can be seen as a symmetric one. It looks quite similar to the cross-limited ratio station structure. However, the cross-coupled ratio structure is not sensitive to measurement noise, as we do not employ any max-min operations. Now, let me present the proposed ratio station formation control structure. We evaluated the formation control structures in a real-world indoor environment. We used two crazy flies as agents and a Kinect camera system for localization of the agents. In this study, we focused only on the XY axis position control systems, and thus our formation control system has to generate the desired roll reference and pitch references. In the proposed structure, we have to first design two position controllers for each agent. We designed PD controllers and employed them to both agents under the assumption that both drones have the same model. The reference signals of the PD controllers are generated via two ratio stations to maintain the distance in the X and Y axis fixed by defining two ratios. We employed the ratio stations presented up to this point. The only design parameter of the blending station is set as gamma equal to 0.5. Thus, it can be seen as a combination of the parallel and series ratio station. In the cross-coupled one, since we assumed that both agents have the same model, the reference generation simplifies to the equations presented on slides. In this case, we set beta equal to 0.5 to make a fair comparison with the blending station. Here you can see the results for the rectangle reference trajectory. Generally speaking, the performance of the ratio station-based formation control structures are quite satisfactory. Let's look at the distance errors to comment more. It can be clearly seen that the cross-coupled one is the best one, both in the x-axis and y-axis. It can be also clearly seen that the maximum error at the transient state is equal to 0.2 meters, which resulted with a pretty nice ratio control system performance, or in other words, a formation control performance. Now let us look at the results for the ellipse reference trajectory. Similarly, the results for this case are also quite satisfactory. Here, I would like to first underline, as the references are varying with respect to time, the ratio performance in the transient state defines the formation control performance. For this case, again, the cross-coupled one resulted with the best performance both in the x-axis and y-axis. Let me now summarize the conclusions of this study. In this study, basically, we revealed that the formation control problem can be handled in the framework of the ratio control, which was pretty interesting for us to observe. We have seen that the presented ratio stations basically define directional or bidirectional communication topologies. We have shown that basically that the ratio control structures can be seen as symmetric and asymmetric formation control structures, which was pretty interesting for a process control engineer. Moreover, in the light of the results, we proposed a ratio station-based formation control structure, and the best performance is obtained from the cross-coupled ratio station structure, as it uses bidirectional communication topologies. As for our future work, we plan to extend the proposed ratio station-based formation control structure to multi-agent systems that are composed of more than two agents. Thanks for listening. If you have any questions, please send me an email. Have a nice and safe day. Thanks.
So yeah, thank you for that presentation. If there's any questions from the chat,
Yep.
or if the author has some comments on their work.
Yeah, I mean, first of all, I didn't know that we will have this kind of question time, because that's why I had this kind of 11 minutes of presentation. The other thing what is really nice that this is like the third paper about Crazyfly. And if I'm not wrong, Tom, your paper will be also about Crazyfly. So we will have this kind of 4 Crazyfly papers. It's pretty nice to see that Crazyfly is used a lot in this kind of academic literature, because as everyone is underlying, it's open source, both in hardware and software. So you can even design your own hardware components. So the question that I would like to ask generally is that which API do you prefer to use, for instance? I mean, for instance, in this study, we used the Python API of Crazyfly, but I know that there is also this kind of MATLAB API, but it's not working that good. So, and there is also this ROS API, I think, for the ROS operating system. So anyone has any idea about which one is better, generally speaking, because I think there is this kind of Bluetooth communication problems from time to time. So you get these kind of disconnections due to the Bluetooth stuff. And personally, we have kind of observed that the one with the Python API works at best, kind of. So if you have any personal experiences about this one, would be nice. This is like one of my first question. Because I think we are just between us. So Dimitri, Halil, Jeremy, Oliver, and Thor, and you. So we can have this kind of Crazyfly discussion, or regarding the paper. This is like one of my students, Mohanam, we came up with this idea about this because I'm teaching process control. This is like, and in process control, we are always talking about ratio control structures and so on. So we had this kind of discussion, okay, can be employed to UAVs. And eventually we have seen that it can be transformed to these kind of different communication topologies. So the stuff that has ratio control using, let's say, for almost 40, 30 years, nowadays it might be called like formation control, agent-based systems. And we just briefly overviewed all these kind of 5 structures and employed them as ratio control structures, which was pretty nice, as I said during the presentation, in the framework of process control, to be honest.
I had one question about your future work. You said that one of the future work is to extend this to several. So I was thinking you could say a bit about what you think are some of the challenges. That.
Oh yeah. So the challenges. Oh yeah. This is like a nice question, because extending these kind of ratio control structures to like multiple outputs, even in the conventional process control area, if I'm not wrong, it's still a challenge. Okay, because over there then. Because basically you are merging 2 outputs or 2 inputs, either dynamically or statically. So now the question is, if you have 3 outputs, how do you merge 3 outputs? So over there, what we came up worked a bit nice, but still work on progress would be like an hierarchical structure. So you merge first the 2 of them, and then you use the fused output to merge it with the third of. However, then the problem comes stability, right? So because the reference signal should be smooth, so you have these kind of different problems over there. So maybe this is not like a nice way to solve formation control. I mean, we have consensus control, all these different kind of structures. So ratio control might not be this kind of perfect path to solve this question, but it is one of the paths. Which I found pretty nice.
Yeah, I think there's some like nice intuition behind it, that in some cases you don't really care about the absolute position
Yeah,
about tier 2. It's more or less to keep the formation you want to have the
exactly.
correct
So,
position.
so this is like as we do in like in ratio control stuff, because you don't want to be exactly on the steady state value, but the ratio between these two outputs should be like always fixed, so that for instance we have this kind of heating problems, for instance air and oil consumption, so you have to keep the ratio in that case, or in gasoline stuff, in the car, in combustion engines, for instance, air and fuel, you want to keep the ratio constant so that you have this kind of high efficient car control system. So yeah, we have 4 more minutes. So regarding Crazyflie, I think it's a pretty nice platform. In that case, I mean, basically you can easily employ most of the stuff directly in a real-time environment. So Crazyflie is pretty nice. And 2.0, I have seen that some of you have used 2.0, 2.1, even 2.1 I have seen, I think, in the paper from the Hamburg paper, I think. From the Hamburg, yeah, I think, if I'm not sure. I think they use 2.1. And in the next one, they use 2.0. So Crazyflie is improving a lot, I think, in that sense. I had no idea about 2.1.
What kind of positioning system were you using again?
We had a Kinect 2.0 camera system. So with Kinect, it was just like pretty easy. And that's why we had this kind of colored balls.
Yeah, so
more simple, yeah.
So how's the accuracy of that kind of system?
I mean, the accuracy depends on the environment a bit, because when you use this kind of color stuff, it's always the environment is important, but the accuracy of Kinect 2.0 is pretty nice, I would say. But obviously you need these kind of anchors or something markers to distinguish, because the depth information is pretty nice. Nowadays, Modem is working on this, like to combine 2 Kinect systems to get a more accurate positioning system. But obviously everything is like indoor in that case.
Yeah.
Right? So this is like indoor studies.
Yes.
Okay, so 2 more minutes. I don't know what to tell more. So I think we can proceed with 2 minutes.
Yeah.
Something will happen. So let's proceed with the next paper. So the next paper will be like, right, reactive-based position control of an under-actuated quadcopter. So let's see the video and then we will have our questions, I think.
My name is Tom C. Anderson, and I'll be presenting our work on reactive-based position control of under-actuated quadrotor here at the European Control Conference 2020. So a bit of background. Up here we have the conventional approach where we have nested loops to do the attitude control. However, in reactive-based control, we don't really have any nested loops at all. What we do have is that the position controllers are injected, or the position errors and velocities are, for instance, injected directly into the attitude system. And then here we're provided a rate feedback for dampening. This is the essentially control structure of the approach in this paper. However, there are other ways of doing reactive-based. The point is that position coordinates are injected into the attitude system. And there's been some previous work on reactive-based control. In this one here, they have the attitude control separated into 2 parts, where tau A is a second-order slide mode attitude controller that stabilizes the attitude along the hover position, near the hub position. And then we have this disturbance signal, which is actually the position error and velocity that is injected into the attitude control system that disturbs or perturbs the attitude system such that it moves towards the desired positions. And also it has a PD controller in the altitude. Another work, instead of a second-order sliding motor controller for attitude, they use a fractional attitude controller, but the injection is pretty much the same, and they use a saturated PD controller for altitude. So our work is different from these in the sense that we don't use an attitude controller. We saturate the injected signal these are not saturated, which means that when the position area is very large, they will inject very large torques in the attitude system. So we provide saturation to that to avoid that. And these are in the inertial coordinates on both the controllers. So we rotate our injected signal to the body frame as well. So our work uses quaternions for the attitude representation. We use it because it's the minimum attitude representation without kinematic singularities, and that it can represent any orientation. And yeah, but the work itself is not dependent on quaternion, so you could use any other representation of attitude as you please. So there's the kinematic dynamics of the control of the system. Here we have the thrust vector, which is 00t, so it's along the z-axis. And here we have the mapping from angular velocities on the propellers to the thrust and torques. And we use Ned frame for the inertial reference frame, and the z-axis points downwards, x-axis points the first rotor, tau 1, on the quadrotor. So the first part of the approach is a translational controller, and it follows the same methodology as most other works out there. We assume that the quadrotor is fully actuated, and then we design a force vector based on this, and then we handle under actuation in the attitude system instead. So we assume that the mass is known and that QMB, the orientation of the quadrotor, is known, and we have some given constant desired position that we want to go to. So this is what the controller looks like. It ensures that the errors go to 0 for any initial condition, and here's the stability proof of that. And it's a PD controller developed using backstepping. So we're going to take this now, and we're going to go over to the attitude control part. And what we do for attitude control is that we take this force controller and we saturate it with some direction preserving saturation function. And in both functions here, this has the same direction as F and U, but it's just that it's bounded by alpha. The max value is alpha. The difference between those two functions, and you can also use other function, the difference is that this one is continuously differentiable, but this one is easier to implement in practice. There are some parameters here, alpha being the maximum value of this one. And then we have the delta here is just prevent division by 0. And KF is kind of how aggressive, how big does the position errors, for instance, have to be before we get into saturation, before we reach alpha. So it's kind of a measure of how aggressive we want the attitude control to be. It represents the maximum torque we can inject into the system. So both alpha has a physical interpretation. This one tells us how big the error has to be before we reach this maximum injected torque. So these two tuning parameters have physical interpretations. So by saturating this and then rotating it into body frame and taking the cross product with 001, we now inject it as a torque into the attitude control system. And then we have our rate feedback adder here that provides dampening. If we use this into the attitude dynamics, then omega BNB is bounded by alpha over k omega. And the proof of that is given here. And eventually you get something that looks like this. And since you know that this is bounded by alpha, you can replace it by alpha, and that tells us that this is negative definite when omega BNB is larger than alpha over k omega. And that's the strategy for attitude control. So kind of like the idea behind it is that this here represents a torque. So it's a vector, and if you then rotate clockwise, counterclockwise around this torque vector, you're rotating from the attitude that the quadrotor has at the moment towards this attitude here, towards this direction. Essentially, the body z-axis, you're rotating it towards the point in this direction. So that is then included in here. And then we have this one, which is kind of like a dissipative term that makes sure that as you rotate towards as the body z axis rotates towards this direction, it will then be dampened and you will settle at that direction. So we're kind of ensuring that we point in this direction without actually tracking it. And that is kind of how we solve the under-actuation. We just have to make sure that the attitude control system is faster than the position control system. And then we will get this this behavior. Another thing is that, well, we can come to that later. What we need to also do is that we need to decide the function for thrust, what the thrust is. So here's two examples. We can say the thrust is defined as the norm of f and u, or as the inner product. So we take the set component of this vector and set that to t. So what is the difference between these? Well, the easiest way to look at the difference is that when you're trying to get your quadrature to go to a point below it. In this case, when the point is below the quadrature, this will try and demand a negative thrust, which is saturated to 0, so which means that the quadrature then kind of like drops down, starts dropping down, and then it will go to the position eventually. But in this case, as long as there is a position error, it will give a positive thrust. So this one will start thrusting upwards, even though it's supposed to go down, but it relies on the attitude controller flipping the quadrature. Right? So 21 is kind of what I would say is more like if with some high gains, it's more aggressive controller, while this one is like a height controller essentially, which can give nice behavior when you're doing like waypoint tracking. While 21 can give better results when it comes to trajectory tracking. So yeah, both of them have been tried with the proposed control approach. So we have some numerical results that we can show. We have the quadrature in 0, 0, 0. We wanted to go to 5, 5, minus 10. So it's up 10 meters and then 5 meters and 5 meters in the XY direction. These are the parameters. We set this here implies that omega is bounded by 5/3, and also that the injected torque is, or the injected position controller does not give a higher torque than 5. So the results look like this. The position error goes to 0. The velocity also goes to 0 because it stabilizes at the desired position. And here's the attitude and angular velocity. Here you can see that there is some, apparently it looks like some oscillations in the angular velocity. What is happening here is that when first the quadrature starts tilting towards the direction it needs to go, but if it starts then thrusting and increasing its velocity towards that point. But if it starts going too fast, it will then start tilting in the other direction to start slowing down, right? So that's essentially the dampening that is provided by this term here to resist the translation motion. So that one actually makes the quadrature slow down by tilting in the opposite direction where it's going and thrusting away from the desired point to slow down. So that's essentially what you're seeing there. That can be how aggressive in that sense it is, can then be tuned by changing the gains. And here's the torque for the quadrature. So in case 2, we wanted to kind of like stress test the system. Here we extended the position control into trajectory tracking controller, and we gave it a circle to track with these initial conditions, and we also injected a lot of noise into the system. Noise on the position, noise on the velocity, and noise on the orientation, and noise on the angular velocity. I think for the position, the noise was essentially plus minus 10 centimeters, and plus minus 10 meters per second on the velocities, and plus minus 10 radians per second. Plus minus 10 degrees per second on the attitude. So it's a significant amount of noise in the system. And we also put in a yaw tracking controller to do yaw tracking as well, to look at the decoupling between yaw motion and the rest of the motion of the quadrotor. The results look like this. Quadrotor goes to the circle. The position error goes to 0, towards 0. It doesn't exactly reach 0. I think it was at about 2 centimeters or something. And then we have the velocity. So you can see there's some apparent oscillations here. That's because of the injected noise into the system. And here is the yaw tracking, as you can see here, for the quadrotor, and then how the error goes towards 0. The yaw tracking error, essentially what we're looking at here. And you can also see here in angular velocities how they essentially go towards become small, and you can see the noise here. And this is then the yaw tracking here that goes to 2 rads per second in the attitude. And then we have the torques, where, as you can see, there's a lot of noise injected. So yeah, that is the work. We can conclude with we presented a reactive-based control strategy for a simplified quadrotor model. It has a very simple structure. It does not rely on knowledge on the inertia matrix. It avoids issues related to topology SO3 because we're not actually tracking an orientation. And the tuning parameters have physical interpretations. So you can kind of like calculate what the gains should be depending on how you want your quadrotor to behave. Future work, however, is testing in experiments. So practical testing of this controller has not been done. So that needs to be done to ensure that it works in practice. But from the fact that it worked in simulations with a lot of disturbances, gives an indication that maybe it can have some robustness properties, even though it's not shown explicitly that it has this. But yeah, so that's essentially what we're working with at the moment is implementing this and testing it experimentally. However, at the moment we don't really have access to our labs, so we're not able to work on it. But the moment we get more access, we will keep working on the experimental results. So yeah, I think that's it, and thank you for your attention.
Yeah, I think I could start with a couple of comments.
Yeah.
The first one, that we haven't tested experimentally, is outdated. We have tested it now on a Crazy Fly 2.0. And it seemed to perform well. And it could, we tried with some disturbances, like hitting it and stuff like that. It would still go back to where it was supposed to go. And in the simulation for the velocity, our injected noise was 10 centimeters per second. I think I said 10 meters per second, which is which is a bit much. So yeah, and the physical interpretation of the gains, they kind of depend on that you're using a physically accurate mapping from thrust and torques to the duty cycles or the angular velocities of the motors. So if you're not using that, then it becomes a bit more tricky to calculate the exact values. But usually it's a scaling factor that you can either figure out experimentally, or if you have I know that the Crazy Fly doesn't use a physical accurate mapping from forces to PVMs. But you can try this out get the scaling factor from either simulations or from some experimental results. And that can still give you then the physical interpretation. So yeah.
How is the performance changing with respect to alpha and KF? I mean, have you played with these parameters? Because, I mean, the system responses, for instance, in case 1 about position error, I mean, it looked a bit slow. I don't know, because of the scale, or do you think it's possible to speed up the system response?
Yeah, I think it's possible to speed it up. So the performance does rely on that. For instance, if your K omega is too large, you're dampening the system too much, it won't be able to orient itself properly, and it will kind of be very sluggish, right? But if you have coma omega too small, there's not a lot of dampening. It will be a lot of very oscillatory, right? So, and the same with alpha. It kind of tells you how quickly it's able to orient itself.
Alpha is like an important parameter, right?
Yes, yes. The alpha is important to set properly. Like you would try and in experiments you would try to keep it small in the beginning, and you would try to like increase it more and more. You notice that in the we don't provide any stability proof of the attitude tracking, because in a sense we're not actually tracking an attitude. We just show you the boundedness of the angular velocities. And so there can be issues, I think, if you set the gains very wrong. You'll observe that with most controls. Yeah. So we implemented on the Crazyfly on the actual.
That's nice.
Yeah. We implemented on the actual platform.
Share a nice video about this kind of.
Yeah. I will. When I have the time, I will go back to the lab and I'll be filming a video. We also implemented. Yeah. We also implemented in Microsoft AirSim.
Oh, that's nice.
Where so we have flying around in the Unreal environment, which is nice. So yeah, so eventually we'll have some videos up and running, and
that's nice. Videos are always nice. That's why.
Yeah.
So do you have any questions from the audience? If not, I'm just going to continue. Let's continue. Okay. So any questions from the audience? Because it's like we have 2 minutes, so I think we can continue. So no.
The topic of the paper is analysis and simulation of route trajectory options for aircraft-type drones. When using drones with a previously known route trajectory, there is the task of forming this trajectory, followed by bringing it on board the drone. The goal of the work is to analyze the possible flight paths, the selection information of space-time parameters that fully describe the path in the form of data arrays, followed by their indication on onboard computer. Based on this data, control actions on board are developed that ensure flight along a given trajectory. There is also a problem of determining the deviation of the current coordinates from the set with subsequent correction. So it is necessary to develop a program that provides a solution to the problem based on the downloaded navigation data. It's important to consider the specifics of the used route trajectories. They consist of typical stages inherent in majority of tasks. Analysis of available open source allows to create a generalized horizontal projection of the route trajectory. In general, it can be considered as a sequence of the following steps: takeoff, climb, sequential movement along the base points of the route, return to the airport, landing. Base points of the route, depending on the task being solved by the drone, can be either distributed evenly over the flight zone. For example, when performing tasks of photo or video shootings, spraying chemicals for agricultural purposes, or represent predefined specific points as which the drone performs a given mission, cargo delivery location. To ensure the task of forming route trajectories, one should proceed from the fact that all typical trajectories can be considered as closed curvilinear contours described in three-dimensional space. Moreover, the individual stages of the flight can be represented in the general case by two projections in the form of segments of second-order curves. Look at figure A. Each point on the contour represents a solution of the space-time problem and determines the geographical coordinates and the height of the center of mass of the aircraft considered as a material point. Mathematically, second-order curves include parabolas, hyperbolas, ellipses, circles, that is all lines which equations contain degrees no higher than 2. The second-order curve has no inflection points. Look at figure B. Straight lines are just a special case of second-order curves. The formula of a second-order curve in a two-coordinate reference system in general form represented on this formula 1. So 5 parameters are sufficient to describe an infinite second-order curve. If you want to construct a curve segment, you will need 2 more parameters. For example, the coordinates of the beginning and the end of the segment. The condition for the absence of inflection points in the selected curved contour should provide a description of the flight of the aircraft as a material point with a smoothly varying acceleration along the axis of the ground speed. Similar requirements are imposed on the sections of the interface between the curved segments that describe the individual phases of the flight. In other words, the task is to ensure the change of acceleration along the axis of the ground speed as a monotonously changing function. A curvilinear contour consists of certain sections, some of which are curvilinear in the horizontal plane. Look at figure A. Y is geographic latitude, X is geographic longitude, and rectilinear in the vertical. H is height, Y is geographic latitude. We will call them turning sections. The remaining sections are rectilinear in both planes. Look at figure B. We will call them sections of horizontal flight, climb, or descent, depending on the ratio of the heights of the beginning and the end of the section. Given that in the general case, the coordinates in the horizontal plane may not coincide with the geographical coordinate system, we introduce the map angle, which determines the direction to the north. Since then forming the navigation posting, the trajectory of the course and directional angles coincide, then the map angle can be taken equal to 0. We also introduce the concept of the trajectory angle for straight sections with climb or descent. Look at figures. For a mathematical description of the separate section of a private orthogonal, we choose the following parameters. Consider the mathematical description necessary to determine the current coordinates of the location of the drone for an arbitrary point in time tx. If they are phi0 and phi k equal on the I section, then the section can be attributed to a straight flight section, horizontal flight, climb, or descent, depending on the ratio of the heights of the beginning and the end of the section. Look at figure 1. If they are phi0 and phi k different on the I section of the private orthogonal, then the section refers to the section of the rotation of the private orthogonal. It is analytically most convenient to describe it with an arc of a circle. Look at figure 2. Considering that for a simulated drone, rotation is carried out at a constant height and at a constant speed. This section is most conveniently analytically described by an arc of a circle which radius can be determined by the formula 2. Where Wi is the angular velocity of the aircraft in the I section, formula 3. Delta VK y is the magnitude of the change in the heading angle in the I section, formula 4. The current values of the geographical coordinates of the aircraft location, latitude and longitude will be respectively determined by formulas 5 and 6. The projection values of the ground speed in the selected coordinate system are determined by latitude, longitude, and height, respectively by formulas 7, 8, and 9. The program provides the construction of generalized flight trajectories of the drone, consisting of straight sections and reversal sections by setting the coordinates of the starting and ending points of the trajectory sections. U-turn occurs at a constant height and constant speed. The program is designed for use in the MATLAB environment and contains a module for determining the current coordinates, which was developed for this environment with the aim of launching the aircraft on board. An example of the given parameter values for the trajectory is presented in table 1. Work with the program begins by entering arrays of coordinate values for all reference points of the trajectory. Entering known values of flight speed and in individual sections is carried out similarly. The remaining speed values are formed from the entered values, observing the conditions for connecting the sections and the conditions for performing turns. The entered speed values are also checked for validity for the selected UAV type. After this, the construction of the trajectory in three-dimensional space with the indication of the numbers of reference points. Look at figure. Also, there is the formation of all data of navigation and motion control, an example of which is shown in table 2. To construct a description of the flight path of the drone, three-dimensional segments of second-order curves were used. For the interface between the sides, it is accepted to change the acceleration of the drone along the axis of the ground speed as a monotonously changing function. A program was developed in the MATLAB computing package, which visualizes the process of constructing a flight path and generates data for navigation and motion control. The developed program can be further improved by including modules that consider the dynamic characteristics of the drone.
Okay. So thanks for the presentation. I think the author is here, one of the authors, Alexander. So you are one of the authors. Your microphone is muted, Alexander. So I'm going to unmute you. Hello. So we cannot hear you, Alexander. It looks like we have some communication problems with Alexander. Alexander, I think you have problems with the microphone. We cannot hear you, Alexander, at all. So I don't think it's right now meaningful to do this kind of question and answer now because we have some microphone problems. Maybe some questions from the chat. From the chat directly, because right now the microphone is not working on your side. At least I cannot hear. So Tom suggested you to rejoin the session. So please leave the session and rejoin, and let's give it a try like this. No. Yeah, I mean, unfortunately, right, Tom, we cannot hear him. It's not just on my side.
Yeah, I can't hear him either.
No.
So it seems to be a
Some
problem on his end. Yeah. But it's to be expected in a virtual.
Yeah, exactly. So I'm sorry, Alexander. So it looks like there will be no question and answer. If there are any questions, please send an email to Alexander. I think you can find it in its paper, all these kind of details. And if there are no other questions, let's conclude the session then. Alexander, we cannot hear you, so I'm going to conclude the session because the plenary session is going to start in 7 minutes. So it looks like everyone left already. Can you type your question in the chat, please? Yes. Alexander, can you use the chat form? Alexander, can you type chat? Yes. Okay. So it looks like it's not going to work, Alexander. I'm sorry. So let's conclude the session. Hopefully next time in the next ECC, let's say 2021, we will come together and laugh about this a lot. But for now, it looks like we have these kinds of communications. Thank you very much, Tom, for helping me out the session. And that's it. Okay, have a nice day. Bye.